Hello, this is Dr. Liu. In this video, I will introduce you universal gravitation. Universal gravitation was proposed by Isaac Newton, although he wasn't able to prove it. What universal gravity is, it's basically attraction between and among anything that has mass. So, for instance, the universal gravitation between Earth and Moon is what's actually keeping the Moon in orbit. And the same thing between the Earth and the Sun basically keeps the Earth in orbit. And our universal gravitation with the Earth actually is the source of our weight, although it's not in the 100% our weight, because the Earth is actually also spinning around its own axis. So universal gravity is something on a grand scheme that keeps the universe together, parts of the universe from drifting apart. What it is not is it is not the force that keeps everything together, such as atoms and molecules and what else in a consistent form. Those are not exactly universal gravity's job. Those are electrostatic forces, for instance. And it's not the job to keep these elementary particles together, such as protons or neutrons. And those are the jobs of the strong force. And also there are weak forces. So universal gravity only is strong enough if you have a very large scale of mass, and usually that also is applying to a large amount of distance. So let's look at an example. Universal gravity, let's have two objects here. This could be the Earth, this could be the Moon. So first we notice there's a distance. This is center to center distance. We're assuming that both objects are uniform spheres, although that's not exactly right. We just make that assumption because their distance is relatively large compared to their individual sizes. So the distance between the Earth and the Moon, that's 380,000 kilometers, give or take. And the Earth only has 6,370 kilometers of radius, so that's a fraction of the 380,000, and the Moon has even a smaller radius. So this is a distance between the two objects. Let's call that r. And each object has a mass, so mass of the Earth and the mass of the Moon. So the universal gravity that binds the two together is dependent on each mass and also their distance. Then additional to that, there's a constant. So the force of universal gravity or universal gravitation is proportional to the mass times the other mass, and then divided by their distance squared, but not without this factor, capital G. The capital G is the gravitational constant. This G has a very small value. (10 to the minus 11th power). And the unit is just the right unit to make all of these units disappear and the result turned into unit of force. So G must have a Newton's unit, and it must have meters squared to cancel the meter squared in the denominator, and then also kilogram squared but in the denominator to cancel all these to the kilogram times kilogram unit. So that is a gravitational constant unit. It really doesn't matter. We always use standard SI units unless you start using different distances than meters, such as maybe kilometers or even astronomical units or light years. Then this unit will have to be changing. I would rather just convert all those different units into meters. So this thing here, it determines how large the force is, and the force is very small if you're talking about very moderate masses such as 2 human beings and some moderate distances such as let's talk about 6 feet, right? So that is about 2 meters away. So let's calculate as an example how much force is there between 70 kilogram human beings that are 2 meters apart. So what is the magnitude of Fg? And by the way, the direction would always be attracting the masses towards each other. There's never a repulsion from universal gravitation. So let's calculate this Fg. So we have the gravitational constant 6.67 times 10 to the minus 11. And we have a 70 kilogram times another 70 kilogram. So the distance is 2 meters and then square that. So it's 4 meters. So that's equal to 6.67 times 10 to the minus 11. And the 70 by 70 is 4,900. And we have 4,900 divided by 4. So let's pop up our calculator and we'll punch this into our calculator. And a trick that I usually use is I will not calculate the 10 to the minus 11, but I'll just keep that in mind. So when I write down the final answer, I can get the right order of magnitude right. And I also keep the 4,900, the thousands away from the calculation. I would just calculate 4.9 times 10 to the third power. So let's write this down before we calculate. So 6.67 times 10 to the 11th power negative, then times 4.9 times 10 to the third power, then divide by 4. So now we only have to do the 667, 49, and over 4. And let's do that. So 6.67 times 4.9 divided by 4. So that's close enough to 6.67, just by a little more. So we have 8.17. Okay, so let's manage that. We have 8.17 times 10 to the, we have a minus 11, we also have a plus 3. So the powers will just add when these powers of 10 are multiplied together. So we have 8.17 times 10 to the minus 8 newtons. So this is in tens of nanonewtons. So it's very hard to measure forces of that small magnitude, and no wonder people don't get stuck together because of gravity. They attract each other. Other than gravity is just not very effective way of getting masses so small to be stuck together. But if we just change the scale to calculate the Earth and the Moon, so let's see, we have another example. The mass of the Earth, mass of the Earth, if I recall correctly, this is 5.98 times 10 to the 24th power kilograms. And mass of the Moon, I think it's about, let's see, 7 times 10 to 22. Let me pause and pull out the number. Okay, yep, 7.35 times 10 to the 22nd power of kilograms. Okay, so we have this. We also have the distance between the Earth and the Moon, usually an average distance of 380,000 kilometers. So 380,000 kilometers. So let's calculate the force between these two objects. Must be a lot, right? So 6.67 times 10 to the minus 11, and the two masses are multiplied together. So 5.98 times 10 to the 24 times 7.35 times 10 to the 22nd. Grab a ruler. And now I want to convert the distance into, oh, that's hard to read, kilometers into meters. So that will be 3.80 times 10 to the 300,000 is already 5, and then kilometer into meter, another 3, and we're squaring that distance. So we're dealing with very large numbers, very small numbers, dividing by very large numbers. I really hate punching all of these powers of 10 into a calculator, and you don't really have to. I'd rather you not do that at all. So this is how I would handle the powers of 10. Again, is to single them out. So this is what I will do. So 6.67 times 5.98. Let's rewrite that. Times 7.35. Then divided by 3.80. That one is squared. Then I will do the powers of 10. So we have a 10 to the minus 11 from universal gravity's constant. 10 to the 24 is positive because it is in the numerator. So is 10 to the 22nd. And then there's a 10 to the 8th power, and also square that. 10 to the 16th power is in the denominator, so minus 10 to the 16th power. So that's in newtons. And now all we have to do is we separately calculate these two portions. So this factor gets calculated with my calculator, and then the other portions just add or subtract. So it's fairly easy. You can use a calculator or not. So let's calculate the first factor in the parentheses. So 6.67 times 5.98 times 7.35, then divided by 3.80 square. So if you have these numbers, you group them together, all these factors, your result is never going to be very big or very small, because these numbers they compare. They're within 10, right? So I got a 20.3. Let's just keep 3 decimal places, 3 digits, 20.3. Okay, so this is 20.3, and then times 10 to the, okay, so I'll do this, 24, okay, minus 16, that's a 6. Okay, it's 8. That's actually 8. Sorry, that isn't, that's 8. So 8 plus 22 is 30. So 30 minus 11, that is 19. That's 19. So it's positive 19. 10 to the 19th power newtons. And I usually just keep a single digit before decimal. So I will shift that decimal to the left, resulting in a factor of 10, additional factor of 10. So 2.03 times 10 to the 20th newtons. So it's a huge amount of mass, attracting another huge amount of mass, and resulting in a very large force that bind the moon to the Earth. Okay, so that may be very irrelevant because we never really get to feel that force. So what about we just we think about something close to Earth, closer. So let's calculate this. We have some space on the right side. So let's partition our page. So think about this. Here we are, this is Earth, and we're standing on its surface. So our weight is mostly the result of our mass attracting the Earth's mass. So let's calculate this. This is our mass. Let's talk about one of those two human beings, 70 kilogram human being. How much does a 70 kilogram human being weigh on the surface of the Earth? Okay, so first we know that the distance is not from the person's foot to the surface. That's not the distance. The distance should be the person to the center. So this is that r, and it happens to be the radius of the Earth being the distance from the center to that person. So this F gravity between a person and the Earth is this m of a person times m of Earth, and divide by radius of the Earth, because that's how far a person is to the center of the Earth, is 1 radius away. Right? And so 6.67 times 10 to the minus 11, and the person is 70 kilograms. Earth's mass 598 times 10 to the 24th, and divided by the distance, the radius of Earth. I should have written this here, so let me write it here. 6.37 times 10 to the 6th power meters. So 6,000, over 6,000 kilometers in radius. So 6.37 times 10 to the 6 meters, and that needs to be squared. So let's practice the same thing here. So we have 6.67, 70 times 5.98 divided by 6.37 squared. Then multiply by 10 to the minus 11, that's from here. And we also have 24 plus 24. And we also have the 6 squared, that's 12 in the 12th power in the denominator, so minus 12. Okay, so let's calculate the values in the parentheses. So we have 6.67 times 70 times 5.98 and divided by 6.37 squared. Okay, so I got 68.8. Okay, so we have 68.8 times 10 to the, okay, so I have minus 11 and 12, that's minus 23, plus 24, so I'll just have that 1 left. Okay, so this is 688. So as we can see, the person's universal gravity against the Earth is this much. And we also know that Fg, this is our gravity near the surface of the Earth, is m times g, right? So this is equal to 70 times 9.8. So that results in approximately, okay, 70 times 9.8. So 686, depends on the rounding, 686 newtons. So it seems like these two are actually related. These are actually related if you ignore the fact that the Earth is revolving around itself, and these two values should be exactly equal. So we can say that here Fg is acting as this F little g. So ignoring Earth rotation. See, part of the universal gravitation should be responsible for the centripetal force, right? So the rest of it will be the gravity, F little g, or weight, W, whichever symbol you prefer. And this really depends on your latitude, right? Because the centripetal force depends on radius, and that is radius, that is distance to the axis of the Earth's rotation. So if you're closer to the poles, then your axis is very short. Your distance to the axis is very short. Right? So you would require a smaller amount of centripetal force. So more of universal gravitation goes into your local gravity. Okay, so now enough talking. Let's use the formula already. So Gm me over r e squared equals mg. This m is the person's mass. So if we divide this out, you get a conclusion that g is equal to gm of the Earth over RE squared. So this is ignoring the fact that the Earth is rotating. If you don't ignore that fact, you need to include a centripetal force, right? And also that centripetal force depends on the altitude. Thank you.